Welcome to homework.
So here in this problem we are given a rigid tank whose volume is given as 0.5 meter cube, and R134 refrigerant is filled in it, and its pressure we are given as initial pressure P1 is 200 kilopascal, and the dryness fraction X1 we are given as 40%, that means 0.4. And now the heat is transferred from the source temperature of 35 degrees Celsius to the refrigerant, and its pressure rises to 400 kilopascal. That means the final pressure becomes 400 kilopascal. And we have to determine three things. First of all, the entropy change of the refrigerant, then the entropy change of the heat source, and finally the total entropy change for the process. So first we will be watching the TV diagram for this process. So this is state 1, this is state 2, and initially the pressure is 200 kilopascal, and the dryness fraction or the quality of the refrigerant is 40 percentage, that means 0.4. So to solve this problem we'll be using the table A11 and A13 to get the input data. So P1 we are given as 200 kilopascal, and X1 is 0.4. So by using the table as per given in the book, we'll be calculating the value of U1 and S1, and one more, the specific volume V1. So we know that U1 is equals to UF plus X times UFG. It should be X1. So UF corresponding to this pressure will be, from the table it will be 38.26 plus X1 we are given as 0.4 times UFG. From the table we'll get the value as 186.25. So after solving this we'll get the U1 as 112.76 kilojoule over kg. Similarly, in this fashion we'll be calculating the value of S1. So S1 will be equals to SF plus X1 times SFG. So again using the same table, S1 will be, sorry, SF will be 0.15449 plus X1 is 0.4 times SFG is 0.78339, and after solving this we'll get the S1 as 0.4678 kilojoule over kg Kelvin. Now next we'll be calculating the value of V1, that is specific volume. So V1 will be Vf plus X1 times Vfg, and Vfg we know it is Vg minus Vf. So we can plug all the values here. Vf from the table it will be 0.0007532 plus X1 we have 0.4, Vg minus Vf. So Vg is 0.099951 minus this one is 0.0007532. So after solving this we'll get the value of V1 as nearly 0.04043 meter cube over kg. So we have obtained all the values at point 1. Now next we'll be calculating the value of U2 and S2, that is at point 2. So the condition, the input data we are given as that the pressure is P2 is 400 kilopascal, and the specific volume will remain same because it's a rigid tank. So V2 is equals to V1, and that is V1 is this one 0.04043 meter cube per kg. So before calculating the value of U1, U2 and S2, we have to calculate the dryness fraction at this point. So X2 we have to calculate. So X2 will be V2 minus Vf divided by Vfg, that is Vg minus Vf. And we have to calculate these value Vf and Vg corresponding to this pressure 400 kilopascal. So again, using the table as per given in the book, we'll get the value V2 we know it is 0.04043. Vf from the table we will get it as 0.000 7905 divided by Vg is 0.051266 minus 0.0007905. So after solving this, we'll get the value of x2 as 0.7853. So we have obtained the dryness fraction at state 2. Now we can easily calculate the value of U2 and S2. So specific internal energy at point 2 or the state 2, U2, it will be equals to UF plus X2 times UFG. So from the table as per given in the book corresponding to this pressure, we'll get the value of UF as 63.61 plus X2 is 0.7853 times UFG is 171.49. So after solving this, we'll get the value of U2 as approximately 198.29 kilojoule over kg. Now next we can calculate S2. So S2 will be equals to SF plus X2 times SFG. So SF from the table will be 0.24757 plus X2 is 0.8753 times SFG is 0.67954. So after solving this, we'll get the value of S2 as 0.7813 kilojoule over kg Kelvin. Now we can calculate the entropy change of the refrigerant, that is delta S of system. So delta of S of system will be M times S2 minus S1. So we have all the values S2 and S1, but we don't have the mass. So mass will be volume divided by specific volume V1. So volume in the equation we are given as 0.5 meter cube divided by specific volume as 0.04043 meter cube over kg. So after solving this, we'll get the mass as 12.37 kg. Now we can plug all the values here. So mass is 12.37 kg times S2 is 0.7813 kilojoule over kg Kelvin minus S1 we have obtained as S1 we have obtained as 0.4678 kilojoule over kg Kelvin. So after solving this, we'll get the entropy change of the system as 3.876 kilojoule over Kelvin, and this value comes out to be as positive because heat is added to the system. That is why this value is coming out to be as positive. So this is the solution for the A part. Now we have to solve the B part. So in the B part, we have to calculate the entropy change of the heat source. For that, we have to calculate the energy input Qin, and for that we'll be using energy balance for the stationary closed system, that is energy in minus energy out, and it will be equals to change in energy for the system. So energy in we have Qin, there is no energy out, so this is 0, and change in internal energy, delta E represents here change in internal energy because change in kinetic potential energy are neglected. So this is M times U2 minus U1. So Qn will be M, we have we know it is 12.37 kg, and U2 we have calculated as 198.29 minus U1 we have calculated as 112.76. So after solving this, we'll get the value of Qn as 1058 kilojoule. So this, the heat transfer to the source will be equal to this value, but in opposite, but with the negative sign, because the direction is opposite. So Q out will be negative of Qin, and this is minus 1058 kilojoule. Now we can calculate the entropy change of the source, and it will be Q out for source divide by the temperature of source. So Q out is 1058 kilojoule, divide by temperature, it is given as 35 degrees Celsius. So if we convert this thing into Kelvin, we'll get 308 Kelvin. So after solving this, we'll get it as 3.434 kilojoule over Kelvin. So this is the solution for the B part. Next, we'll be solving the D part of the the C part of the problem. And in this part, we have to calculate the total entropy change. That is delta S for total, and it will be equals to delta S of system plus delta S for the source. So system we have calculated as 3.876 plus this one is for the source we have minus 3.434. So after simplification, we'll get the entropy as 0.441 kilojoule over Kelvin. So this is the answer for the C part. So I hope you got the problem. Thank you.